And now we get to a really exciting part in our exploration of integration, where we're starting to talk actually about some very deep ideas. And our objective right now in this video is to establish the comparison test for improper integrals, which is a result that we can apply to determine whether a particular integral converges or diverges without having to calculate it at all. So it's actually quite powerful. But the other thing that's really cool about this is that this hints at some of the ideas that we're going to explore further in the chapter on sequences and series. There's a similar result called a comparison test, but it's for series. So some of the ideas that we're developing here are going to reappear in that section, so just keep an eye out for that. We do need to first talk about we need to review basically some ideas from the first calculus. So first, we need to talk about comparison of two limits. In this case, we're talking about specifically about limits at infinity, but it applies really to any kind of limit. It's just we're talking about limits at infinity in this case because we're talking about improper integrals. So in chapter 2, the limits chapter, we saw that if f of x is a function that's greater than or equal to g of x, so it's at least as great as this function, other function g, for all x greater than a. So at some point on the real number line, f overtakes g and just g never catches up. Then the limit as x approaches infinity of f of x is strictly greater than the limit, or is greater than or equal to the limit of as x approaches infinity of g of x. So a visualization of this would be, we have our two functions. Let's call this one f of x, and this one's going to be g of x. And regardless of whether either one has a limit at infinity, so one could blow up, one might not, but at the very least we say that given we know that f is always going to be greater than g, right, so it's the function values are larger than the function values for g, then the limit at infinity of f has to be at least as great as the limit for g, regardless of whether both or none or just one of them converges, even if both of them are infinite. So let me just say that, even if both are infinite, which is the most boring example, I guess. Take that with comparison of two integrals. Oh, before we can move on, let's, visually, what are we talking about? We're saying if the blue curve never goes below the red curve after a certain point, then the limit at infinity of the blue curve has to be greater than the limit at infinity of the red curve. Asymptotic behavior is larger. In chapter 5, we saw that if f of x is greater than or equal to g of x, which is strictly greater than 0 for all x in an interval, so over a to b, f is larger than g, then the integral from a to b of f of x dx is greater than or equal to the integral over the same interval of g of x. And so visually, now let's visualize what's going on here. What we're saying here is we fix some a and some b, and we have some function f, which is always greater than g over that interval. Actually, let me make it a little bit more clearly, just so you can see that. So the area under the red curve, another way of thinking about this, is going to be less than the area under the blue curve. Makes sense, right? That's all we're saying. Okay, but these two things we can put together to suggest a very powerful result for improper integrals, and that's what this next statement is. So the comparison theorem for improper integrals which our shorthand is to call it the comparison test. What it does is it helps us, it tells us something about the convergence or the divergence of an integral given some other benchmark integral. So given some comparison integral, whether it converges or diverges, we can test whether some other improper integral that we're actually interested in converges or diverges. All right, so let's actually, you see the statement then. So the statement is, let f and g be continuous functions and we suppose that f of x is greater than or equal to g of x, but both are positive for x greater than a. Okay, so at some point, as you move left or right on the x-axis, the curve f is above the curve g forever. Then we have two cases. First case, given the integral a to infinity of f of x dx converges, we also have the integral from a to infinity of g of x dx convergent. So let's very clearly discuss what the logic here is. So this is what would have to be true. So if that is true, if we know that that's true, then that guarantees the improper integral of g of x is convergent. So the implication, or the logically what would have to follow, okay? Case 2, given the integral from a to infinity of g of x dx diverges, we also have the integral from a to infinity of f of x dx divergent. Same idea. What we assume to be true is the divergence of the integral of g. And that implicates or implies that the integral of f also diverges. Third case, which isn't really a case, but it's like the disclaimer at the end, is if neither. So if neither the integral of f converges nor the integral of g diverges, we can't determine anything. Anything further, sorry. So this test is inconclusive. It just means you have to try again with another benchmark comparison. So let's visualize this, okay? So that we understand what we're working with. Okay, so I'm going to suppose that my red curve, okay, again is see what colors we're using here. Okay, so G was, this is my G curve, okay? This is going to be my F curve. And at some point A, F overtakes G and is always greater than. Okay, so this is what the statement is saying. So if the blue area converges, if the blue area is finite, so is the red area. And that makes sense, right? Because the red area is this whole tail, and it's contained in the blue area. So even if you go out to infinity, right, which is what we're doing here. On the other hand, if the red area is infinite, so is the blue area. Okay, so if the red area is infinite, that integral does not converge, then the blue one has to as well, because it's larger than it. So of course it has to be infinite, and that's the power of it. Now, if the red area is finite, that doesn't tell us anything about the blue area. If the blue area is infinite, that also doesn't tell us anything about the red area. So there's really 4 cases to consider here, but the case 3 and 4 are wrapped up in this one. Okay, so if that's the case, then it's both of them are giving us an inconclusive test. Okay, so we won't give a proof, but the rationale, we can, you can ask me about it. It's not too complicated. In fact, we could probably do a proof sketch pretty easily, but for the sake of ease and time, we're just going to skip that, and we're going to move into in the next video, we're going to